Hello, welcome to lecture 7. At the very end of our last lecture, we did an example where we found the electric potential around a conducting sphere of charge. We found it outside, on the surface, and inside. That might put you in mind of a Van de Graaff generator, and that's the video I'm playing here on the screen. The sphere gets all charged up by a little belt that goes around and around. So the kid gets all charged up. There's an electric field all around him, and eventually, once the charge gets so high, his hair just pops right up. We're going to see that just a second. Okay, there we go. Okay, that's pretty nifty. Once we're back on campus, maybe I'll be able to bring the Van de Graaff into the lab if anybody wants to try it out. So we're going to use this as a springboard and start thinking about ionization and corona discharge. There's a nice discussion about this in your textbook if you want to read along. Let's start with the idea that air experiences something called dielectric breakdown, and that happens when the electric field hits a maximum value of about 3 million volts per meter, 3 times 10 to the 6 volts per meter, or newtons per coulomb. That means when it hits dielectric breakdown, it means that the air becomes a conductor and the charge will actually travel across the air. This inherently limits the maximum potential on a conducting sphere. So if V is equal to kq over r, and E is kq over r squared, then V is equal to the electric field times the radius of the sphere. Once the electric field hits 3 times 10 to the 6 volts per meter, so right here, if we're charging something up, once your electric field hits that maximum value, all of the extra charge that we're trying to put on the conductor, it's going to leak off into the air. Let's have a look at what that means. Here's a video I filmed down in the lab.
This demo is called a Wimhurst machine. If you look, you see it has a hand crank on the back. I'm going to turn that. We've got some brushes here and some brushes here. When I turn the crank, the wheels are going to move in opposite directions. That's going to gather electrons from the air. It stores it in these two jars here. Those are called Leyden jars. And then, because we have equal and opposite charge stored in the jars, these spheres are going to get equal and opposite charge. So let's see if you can guess what's going to happen between the spheres as I spin the wheel. Now, I don't know if you can see it. Maybe you can hear it. That snap is a spark that goes from one sphere to the next. Let me just try and zoom in. Okay, hopefully you could see it when I really zoomed in there. That's a small version of how lightning works. So the charge builds up, the electric field increases. Once the electric field gets so big, you get a dielectric breakdown of the air, and you get a spark hops from one sphere to the other.
Okay, so there's a demo that you can actually do that shows what happens when the charge travels across the air. That's a spark, and really big sparks are lightning. So another implication of all this, if we just rearrange our equation, we can see that the electric field is the potential divided by the radius. That means if we have a small radius for a conductor, the electric field is going to be higher. In other words, electric field is bigger for pointy objects. An example of that is a lightning rod. A lightning rod is a big metal spike that sticks up out of the top of your house. We don't have tons of them in Newfoundland. Places with a lot more electrical storms do have them. But lightning rods stick up out of your house. They have a higher electric field compared to your house itself because they have such a steep radius of curvature. So they attract the lightning. The lightning hits the rod and dissipates it to ground so that everybody and the house itself is all safe. Pretty neat. Let's take a little time now and discuss equipotential lines, something you probably covered at least a little bit in Physics 1051. Equipotential lines are a way to visualize the electric potential and the electric field around a charged object. Equipotential lines are exactly what they sound like. They're lines with constant potential. Geography lovers might find it useful to make an analogy with contour maps. Here I have a picture of Mount Fuji, and here is a picture, just with two views, 3D and a top view, of a contour map of Mount Fuji. So the lines here show the height. Everywhere on this lower red line, the height is 2,000 meters. Everywhere here, the height is 2250 meters, everywhere here it's 2500, and so on. Something these lines can tell us is how the height of Mount Fuji changes. If the lines are close together, for example right here, the height changes very rapidly. It gets steeper, so it's very steep. If the lines are spread out, the height doesn't change very rapidly. It's more shallow, it's closer to level. So like a contour map with contour lines show the height of Mount Fuji, an equipotential map with equipotential lines shows the electric field around a charge. To get started, let's think about a positive point charge. We know the electric field lines are radially outwards, so they point out in all directions. And we know that the electric potential around our point charge is given by V equals K times the charge divided by the distance from the charge. So an equipotential line is a line with constant V. To get constant V, we have to have constant R. That means an equipotential line will be a sphere or a circle in our 2D drawing, a sphere in a three-dimensional drawing. Okay, so everywhere on this line that I just drew, it would have the same value of R, so it'd have the same value of V. This is an equipotential line around this charge. Okay, let's go on to the next slide. Let's draw a few more equipotential lines. Let's draw them kind of to scale and make some conclusions about equipotential lines and electric fields. Let's get to drawing some equipotential lines. I've reproduced my diagram here, except I drew my electric field with the computer just because it looks nicer. Let's say that our charge here we have in the center is positive with a magnitude of 0.111 times 10 to the minus 6 coulombs. And let's say that our graph paper here on the screen is 1 meter corresponds to 1 block. Let's draw some equipotential lines. So we know that our electric potential V is KQ over R, and to get equal potential, we're going to need equal distance, which means it's going to be a circle for our equipotential lines, and R is going to be equal to K times Q divided by V. Let's get some lines here on the graph. So let's say our first potential we want to draw, or our first equipotential line, has a potential value of 1000 volts. That means that R, which is going to be K, 8.99 times 10 to the 9, times Q, 0.111 times 10 to the minus 6 coulombs, divided by 1000 volts, is going to give us 1 meter. So our first equipotential line is a circle with a radius of 1 meter. There we go right there. So this line has a potential of 1000 volts. Anytime we're this distance from the charge, the potential is 1000. Okay, for our next line, and our potentials are always our equipotential lines are always evenly spaced in potential. So say our next line has a potential of 750 volts. That happens if R equals 1.33 meters. Let's draw that one next. My circles aren't the best, that's why I pre-sketched them with PowerPoint. This one is 750 volts. So everywhere on that line it's 750 volts. My next potential will be 250 volts lower. That happens at a distance of 2 meters from our charge. So that line is here. Now that we have 3 lines drawn, we're starting to see a behavior in our potential. And then for our next line, let's say our potential is equal to 250 volts. That happens if R is equal to 4 meters. And that's all the way out here. That's pretty close to the edge of the graph, so I'll stop drawing them at this point. But you could keep going, no reason not to. 250 volts on this line. So what are some conclusions we can make? We know that electric field is going to be strongest in close to the charge. So that's definitely true. And we know that electric fields are strong where the electric field lines are close together. Turns out the electric field is strong where the equipotential lines are close together. So here, the equipotential lines are close, and E is strong. Places where the equipotential lines are spread out, the EPL lines are far apart, here's where the electric field is weak. And another thing we might notice is that the electric field lines are perpendicular to the equipotential lines. So E lines are perpendicular to equipotential lines. So this is all certainly true for this example, and this is true for fields and equipotential lines in general. On our last slide, we could see that equipotential lines were perpendicular to electric field lines. We also saw that the electric field lines pointed towards lower potential. We can discuss those things in terms of the relationship of the equation between potential and electric field. So first, about the electric field lines pointing towards lower potential. Electric potential, delta V, the change in potential, is negative the integral of E dot ds. Well, what this means is if your electric field is parallel to your path, if you're going in the same direction as your electric field, this whole bit will be positive, which means your delta V is going to be negative, which means your V final is smaller than your V initial. So if your field and your path are in the same direction, your V gets smaller. That means electric field points towards lower electric potential. Okay, for the perpendicular stuff next. The E dot ds, the term inside your integral, that's a scalar product. That's equal to the magnitude of E times the magnitude of ds times the cosine of theta. Well, I'm giving myself away here thinking about 90 degrees. Cosine of the angle between E and ds. If your electric field is perpendicular to your path, perpendicular to ds, then theta equals 90 degrees. Cosine of 90 is 0. So delta V equals 0. Delta V equals 0 means V final equals V initial. That means V is constant. That means it's an equipotential line. So anytime your electric field is perpendicular to your path, your V is equal to constant. On the flip side, if your electric field is parallel, or even just not perpendicular, then your delta V would not be 0. Your potential would change if you moved parallel to your path. Okay, next we're going to move on. Oh, one last thing. I've got some equations here. Since the potential is the integral of the electric field, it means that the electric field is the derivative of the potential. We discussed this a bit before in the previous lecture, so I won't go through it again. We'll just do a reminder that any component of the electric field is the derivative with respect to that component. Electric field is a vector, so in general that would always have to be given with direction.